Hi everyone, my name is Patrick Schwanchera. I'm a postdoc in Silke White-Sentence Group at the University of Nottingham. I'll be chairing today's seminar, which will be given by Chris Westbrook from Laboratoire Charles Fabry in France. Chris did his PhD at the University of Michigan. Then he spent some time at the National Institute of Standards and Technology in Gatesburg in Maryland. And then he took the position as a researcher at the French National Center for Scientific Research in the Laboratoire Charles Fabry. And Chris is now going to give us a talk about the simulation of early universe with Bose-Einstein condensate. So Chris, please, the floor is yours.
Okay, thank you very much. And thank you for this invitation. I noticed that the titles I've written here are not the same as the one I submitted when I wrote a title. I guess probably at the time I was thinking in a more narrow fashion than I have been in the last few days. So here I have a more expansive, maybe sexy title. But you can all tell me later on if you think which you think that was the correct title. So we can think. So what it's all the same experiment, but you can think of it in terms of simulating particle creation in the early universe, or the way I understand it the best is as an acoustic analog of the dynamical Casimir effect. And I'll sort of talk about both of those little aspects. I'll start with the early universe, even though I don't know all that much about it. So here's sort of a simple-minded vision of particle creation in the early universe. There's a picture that I picked off the web somewhere. The idea is you have the universe which inflates, which is due to this thing called an inflaton field. And at some point this stops and the inflaton field enters this, this picture here, this sort of potential energy well, and begins to oscillate in this well, in this effective well. And what that does is it causes a parametric instability, which creates particles in pairs, and presumably in entangled pairs. And as I understand it, this is often referred to as preheating in cosmological scenarios. And then after creating all these entangled pairs, they continue to interact. There's spontaneous decay, there's decoherence, there's thermalization. And the universe then eventually evolves into something that we would recognize today, more or less thermalized distribution of matter and radiation. And that second phase is called, often referred to as reheating, which is a rather confusing terminology, but I'll get back to that a little later. All right, and then the idea of particle creation is really ubiquitous in quantum field theory, because particle production accompanies any sudden modification of boundary conditions for a field. It's an old subject, and I've got some old references that I've written here, but there are many that I can hardly do justice to. I will just mention one case that's I think is kind of fun and interesting, and very concrete. It refers to a calculation done by these people at the Laboratoire, it's called the LKB, Castel in Paris, in which they thought about what would happen if you had an optical cavity or some sort of electromagnetic cavity, and then took one of the mirrors and made it oscillate very rapidly. They did a calculation for the number of photons what would happen is it would create pairs of photons, the sum of whose frequency is equal to the driving frequency omega. And they calculated a rate for a cavity with given finesse f. And this rate is very small because it's suppressed by this v over c squared factor. Okay, so that's just a calculation. Realizing this is not so simple, although there have been ideas and even realizations that have been have been made in the recent past. It is possible, actually, using the nonlinearities in a Josephson junction to effectively move the mirror or move the termination of a transmission line at a very high frequency. And an experiment was done, more than one experiment has been done like that, demonstrating the creation of pairs of photons. Another idea that was proposed was that you could, instead of moving a mirror, you could place an index of refraction, a material with an index of refraction that you could modulate in between the mirrors, and then modulate this very rapidly. The idea is that some semiconductors might be able to do this at very high frequencies, and then thus get over this this V over C squared suppression. I'm going to talk about a completely different system, Bose-Einstein condensate, in which the particles which we're going to talk about are phonons and not photons. And there, the idea is a bit analogous to this changing the index of refraction idea, in the sense that we have in this BEC, for the phonons, we have a speed of sound, which is given by this formula here in a weakly interacting Bose-Einstein condensate. It depends on a scattering length A, a density rho, and inversely proportional to the square of the mass of the particles. And these things in red, all these things in red can in principle be modulated, in principle quite rapidly. The coefficient A by a Feshbach resonance, the density by somehow squeezing, changing the shape of the Bose-Einstein condensate. And that's what I'm going to be talking about. And it is even possible in principle, although I've never seen it done, I'm actually dreaming of doing this ourselves, to place the atoms in the condensate, place the condensate in an optical lattice, which would modify the effective mass of the particles. And then by changing the depth of this lattice, you could modulate the effective mass. Okay, so we're just going to talk about changing the density. And then what happens is that we will do this at some frequency omega, and then we will produce phonons at the sum of these frequencies. And the symmetry of the problem, it dictates that the K vectors of the two excitations have to be equal and opposite. So omega 1, in our problem, omega 1 will be equal to omega 2 here. And so the reason to do this in a BEC is that you have the possibility of getting to very low temperatures and possibly having vacuum fluctuations be very important. Well, I was going to say there's all these systems have dirt in them. They're not nearly as ideal as what one writes down when you do a calculation such as the one on the previous slide. And the important bit of dirt in our experiment is that there's a finite temperature. But we've been able to get the temperature down to something which we estimate to be around 30 nanokelvin, which at our modulation frequency, which is about 2 kilohertz or 1 kilohertz for the phonons, corresponds to a thermal population of about 0.25. So we're getting close to a situation where we are in a situation where the vacuum fluctuations dominate the thermal fluctuations. So that's going to be important in what follows. Now, of course, you don't need to do this. I mean, the idea of parametric oscillation is much older than quantum field theory. It corresponds to what is often known as Faraday waves, discovered by, I guess, Faraday. And an interesting example that you can find on Wikipedia is what you generate when you have a container of water that you place on a vibrating table. You generate these waves in a process that is highly analogous, or if you like, the same as what I've been speaking of in these quantum systems. And this is a really interesting topic, and I don't need to convince people in Nottingham, nor in Poitiers, that this is a really interesting thing to study, despite the fact that you're dealing with a classical fluid. There are a whole lot of interesting and pertinent effects that happen here that can be studied as well as in the Bose-Einstein condensate or the other systems that have been used. Okay, so now getting back to BECs, I'll just give a quick overview of things that I know about that have been done. Actually, the earliest experiment that I know of dates from 2007, in which Engels and his group did exactly what we're doing. They modulated the transverse confinement in a magnetic trap. And then in just in situ images of the cloud, they demonstrated that they had waves that were being generated, which corresponded to these this parametric instability. In 2012, our group did very much the same thing, with the difference that we detected these excitations in momentum space. So we detected K vectors and pushed this whole analogy a little further. And what I'm going to talk about today is actually just an improved version of the experiment we published in 2012. And actually, I don't know how many people, there might be people here from the, that were in Nottingham 12 years ago. Actually, I spoke about this experiment in Nottingham, I believe, about 12 years ago. But now we have some new things, and so that's the title of that's the topic of the talk. But I also want to mention that in the meantime, there have been some interesting results that have been done by modulating the scattering length in an interacting condensate. So there are several groups that have a disk-like geometry, as is shown in this picture here. They modulate a magnetic field, which causes the interactions between the atoms to be modulated, and have observed a lot of interesting effects. A very spectacular one are these correlated jets that come spitting out of these out of this modulated condensates, very much like these essentially back-to-back momentum particles with momentum going directed back to back. And in a variant of this problem, a group in Purdue has actually shown that they have evidence for these such excitations being entangled. And finally, I have been hearing about the Heidelberg group led by Markus Oberthaler, that has also been doing a similar geometry with a similar Feshbach resonance to modulate the scattering length, and have also gotten interesting results pertaining to particle production. So now I'm just going to concentrate on our stuff. And before I do so, I would like to acknowledge my collaborators. There they are in a picture. This group is this work is actually largely the content of the PhD thesis of Victor Gondret, who is working on writing up his thesis. So if you want to know more, in 6 months there may be a long document describing this work. And we've also had a lot of input from two theorists, Scott Robertson, who is now in Poitiers, and Amaury Micheli, who is now in Japan, and who was a PhD student of the late Renaud Parentani. And I'd like to mention that Renaud actually had a lot to do with encouraging us to pursue this work. And I will mention some of the results that these three people have had that have influenced our experiment. Okay, so here's the experiment. There is a BEC that's trapped in a laser trap, and we modulate this BEC by taking the laser and simply periodically modulating its intensity, as is shown on this red curve. We modulate it for a while, then we stop, and then wait. What the BEC does, it begins to respond to this modulation, and if we excite close to the transverse trapping frequency, we actually excite a breathing mode in this condensate, and this will continue to oscillate even after we stop the laser. So the experiment is going to be to excite this breathing mode and then allow this breathing mode oscillation to act as the parametric drive for this particle production. So this is exactly what we did, or very close to what we did in 2012 with Jean-Christophe Jascoula. And I should mention that the experiment was actually inspired by work by Jacopo Carosotto and his collaborators. And what's new is that we've made a few innovations that have improved the experiment. In particular, the atoms are now in a cross dipole trap, not in a simple one like that. And that has allowed us to better control the number of atoms and lower the temperature. And then we use the same detector we've used in the past, that is to say, a microchannel plate which detects the arrival of these atoms. And the arrival of these atoms is, well, the detector has a danger of saturation when a BEC hits it. And so we have taken steps to circumvent this problem by scattering away a large fraction of this BEC so that we can concentrate our efforts on analyzing the particle production, these side bands, which I will talk about in a minute. Okay, so the detector is really important, so I'm going to talk a little bit more about it. What we do is we use metastable helium atoms in this 2 triplet S1 state, which is metastable and has an energy 20 electron volts above that of the ground state. So when they hit an object like the metal plate, the metal surface of this microchannel plate, they have some efficiency for emitting at least 1 electron, and the microchannel plate is then able to collect them and amplify them. And in this way, when we release the atoms, they're in this small trap here, they fall down onto the detector, and a fancy anode behind the detector allows us to detect the arrival time as well as the transverse positions of the atoms. And since the initial condensate is very small, very small compared to the length of this fall, the positions and times we detect on this detector allow us to accurately reconstruct the velocities that the atoms had when they were released. So I'm going to sort of interchangeably talk about arrival times and velocities in this problem. The detector then allows us to reconstruct individual atoms, and we can make pictures like the one shown here, where each dot actually corresponds to an atom that landed. The thing in the middle is the BEC, which looks a little funny because it's partially saturating the detector. And above and below it are the side bands due to this particle creation. That is to say, particles that have been created with a slightly higher velocity than the BEC and ones with a slightly lower velocity than the BEC. The detector has a quantum efficiency which we estimate to be between 20 and 50%, and that's going to be important later. And so you can see how the experiment proceeds. We have this BEC. We modulate the laser intensity. Typical modulation frequencies are 2 kilohertz. We let it oscillate. Then we turn the trap off. The atoms fall, and then we reconstruct distributions like this one. I should mention that in this experiment, when we don't modulate too hard, and we adjust the trap well, the transverse distribution is pretty close to being single mode. That is to say, the size of the cloud that we detect is pretty close to the diffraction limited size of the known transverse size of the trap. Okay, so for the rest of the talk, I'm going to pretty much ignore transverse effects and concentrate only on the longitudinal velocities of these atoms when they hit the detector. All right, so next. So back to the experiment. So I've already shown you the trap and the modulation. And when you do all this, you see these two clouds hit the detector, and these three clouds hit the detector, and you get spectra that look like this, a time of flight spectrum, where now I'm plotting numbers of atoms as a function of their arrival time. Okay, so 307.5 milliseconds is the time it takes an object to fall at rest, to fall these 46 centimeters to the detector. And what we see on each side are these side bands, atoms that have been emitted with a slight in opposite directions opposite directions longitudinally relative to this condensate. The scale, the condensate is not to scale, because in order to avoid saturation, we have eliminated about 95% of it using Bragg diffraction. So we hit it with with laser beams to get as much of it away from the center of the detector as possible. It lands later on. I won't show it to you. And that allows us to study these two side bands in a relatively unperturbed by what's going on here. All right, so that's the experiment. And now to analyze this data, there's an important other effect that I have to discuss. It is known as phonon evaporation, at least according to the authors of this paper who introduced the idea. And it has to do with the fact that, well, when you detect, the detector detects atoms hitting the microchannel plate. However, what we are exciting in the BEC is, in principle, are not just atoms, but quasi-particles, excitations, phonons, collective excitations inside this interacting gas. And the important thing about this work here is that they showed that in many situations, the quasi-particles of momentum k adiabatically transform themselves into atoms, which we detect with the same vector k. And the way you can understand that is to think about creation and annihilation operators for the atoms, AK and A dagger K and minus K. And think about how the Bogoliubov transformation relates the phonon operators C to these atomic operators A and A dagger. And in the long wavelength limit, small k, the weights of this V and U, these V and U coefficients are approximately equal. Whereas when the k vector gets large, the V part of this thing vanishes, and particles are practically equivalent, or the quasi-particles are practically equivalent to atoms. And the important thing here is the boundary between low k and high k depends on the density. So as you let the condensate expand, this boundary moves, and it will move past a given k vector, and that's how an atom, a quasi-particle, transforms itself into an atom while preserving its k vector and preserving, importantly, its statistics. This works provided there's a certain adiabaticity going on, so it doesn't work for very, very low k vectors. But in the range where we use it, we can show that this argument actually holds up. So the way the experiment works is we're going to detect the atoms. We're going to get their velocity. And then from that, we deduce a k vector, a momentum vector. And knowing the oscillation frequency at which we modulate the condensate, we can then work out an experimental dispersion relation for these atoms and deduce the speed of sound. So here's an example of that. On the left, you see a time of flight spectrum, which gives you a number of atoms as a function of the detected velocity. Now I've given you it in terms of a velocity relative to the condensate. And here I'm plotting the detected velocity as a function, or I'm plotting, the independent variable is really the excitation frequency, but I'm putting it on the horizontal, on the vertical axis. And so now you see the modulation frequency, omega modulation, as a function of the detected velocity. And so, or which we can convert into a momentum. And from this, you can determine two things. You can measure the speed of sound. And more importantly, or equally importantly, there's a coefficient alpha here, which you can demonstrate experimentally is equal to 2, which is 2 because the excitations that we create have frequencies that are half those of the modulation here. Okay, and so once you have this alpha, you can figure out what the speed of sound is. Here's an example where the speed of sound was 60 millimeters per second. Later examples are going to have somewhat smaller speeds of sound because we worked at lower density. Okay, so there's the there you have the dispersion relation. And so knowing all this, we can now take a closer look at the data that we get when we do this excitation. And here I'm showing 5 different curves in which we excited the atoms for different durations. Okay, the procedure was first to allow the laser to modulate over 6 periods at 2 kilohertz, stop the laser, and then allow the condensate to continue to oscillate for 4, 6, 8, 10, or 12 oscillations. And the longer we wait, you see, the more particles, or the more quasi-particles we produce. You also, if you look carefully, you could maybe see an exponential growth. I'll go into that a little on the next slide. And as you pump harder or pump longer, you see that not only do the peaks go up, but they shift and broaden. They broaden in this asymmetric fashion, which we don't really understand. That's work in progress to figure out why that's happening. Okay, and then if you want to look, we can look at this exponential growth a little bit more closely by showing this is a different data set, but here again I've plotted the number of atoms in one of these peaks as a function of the number of excitations. And at least for part of this range, we do see a sort of exponential increase in particle number, at least for a decade or so, confirming that we have something like an exponential growth in the right conditions of these particles. And the data that I've shown also allows us to, like I said, back out an approximate value for the temperature. And there's where this thermal fraction comes from. This calculation then gives you an estimate for what's the thermal fraction of the atoms of excitations at this temperature. Okay, and then now, so we're doing this parametric excitation, and so what we expect we're creating is a 2-mode squeeze state, which I'm going to write like this. TMS stands for 2-mode squeezed. And it is a superposition of different populations of different but correlated populations of the K and minus K modes with these coefficients, which are written here, all determined by a single parameter known as the squeezing parameter R. That's what we expect. So one thing that is fairly easy to do is we can test part of this by tracing over one of the modes, looking at the population of only one of the two modes, and seeing if we get what we expect, namely a thermal distribution, that is to say, a power law distribution of particles of the number of particles in a single mode. And here you see an example of such data. And you see on a log plot that this distribution does indeed look like a power law. We can deduce from it a mean number of photons. And I have plotted also in this brown thing a Poissonian distribution with the same mean. So you see they're very different. And so this at least corroborates the claim that we should be producing a two-mode squeeze state. It also does another thing for us, because we get this nice exponentially, or I'm sorry, logarithmically, well, what am I saying? Power law dependence of this population. It confirms that in the area over which we took this data, we really are looking at a single mode, a single K vector, or something close to it, of this distribution. Because if we were looking at several modes at the same time, this distribution would not be nearly as simple. It would be a more complicated distribution. In the limit of a very, very large number of modes, in fact, becomes Poissonian. It would look like this dotted dashed curve. So that's an important thing to confirm, that we can really look at a single mode. Okay, so now the interesting thing is how about that? How about these non-classical effects? Since we're now claiming that we are able to create these particles mostly from vacuum fluctuations and not thermal ones, we'd like to see if it really is non-classical. So a simple, straightforward thing to look at is the variance in the number of particles that we see in each of these two modes. To normalize it, I will take this variance and normalize it to the shot noise. And if you normalize it in this way, you would expect this variance to be greater than unity for a classical state. And on the other hand, for a two-mode squeeze state, given a perfect detector, you expect this variance, in fact, to vanish, because nk is always equal to n minus k each time you repeat the experiment, even though nk itself is different on each shot. It doesn't actually, we don't expect it to really vanish, because we have a finite detection efficiency. If it's a 20% detection efficiency, which is kind of what I suspect it is, that means this variance cannot go below 1 minus 20%, that's to say 0.8, okay? And now we've discussed, well, I'm pretty sure this is a signature for a non-classical state. Whether it is really a signature for entanglement has been under some debate in our group, and I'm not sure we have a perfectly clear answer to that. But this discussion has inspired us to look a little further for other kinds of entanglement witnesses. And Denis Boiron, my colleague, inspired by work by Geza Tot, has discovered that there is a entanglement witness that we can really use to claim that we have entanglement for these states. Entanglement is another variance of a quantity that looks a little similar. There's an nk minus n minus k in it, but it gets multiplied by the number of particles as well. And it's normalized in a different way, so it's dimensional. Well, it's normalized in a different way. What can I say? This thing is expected to always be greater than unity for separable states as well. And so if it goes below 1, it should, under certain circumstances, we ought to have an entangled state. So what does that give? Here I'm showing you, again, the same data I showed you earlier, just to reinforce the fact that we're going to have I'm going to show you five different data points corresponding to these 5 different runs. Okay, and then when I do that, there are the 5 data points. On the top graph, I've shown you the normalized number difference variance. And there you see that for certain, and I've done it as a function of time rather than number of oscillations, but this 2 milliseconds corresponds to 4 oscillations at 2 kilohertz. And you see that there are, at short times, we do indeed find a sub-Poissonian number difference, and this entanglement witness does indeed go below unity. Whereas if we wait longer, it seems to go away. This non-classical signature has disappeared. Now you might say that, well, this is all hanging on one point here that's really decidedly below the variance, but below this threshold of unity. But I want to emphasize that it's actually, we've repeated this many times, and it's quite robust and reproducible. Here is another plot where the full circles are the same ones as you saw on the previous one. And we've included a bunch of other runs that we've done. They're a little difficult to all put on the same plot because on different days we have different number of atoms. That means a different gain and different conditions. Victor Gondry has tried to rescale the time of these other runs in such a way that they can be plotted on the same plot. So here they are. There's a bunch of there are horizontal error bars here now, which reflect an uncertainty in this rescaling that Victor did. But you can see that in the vertical direction, we have several instances for relatively short excitations that we go below this quantum threshold, or in this case, we want to say I'm arguing the entanglement threshold. So it's a fairly robust effect once we get everything working right. Now we can say a few words about theoretical expectations. There was actually Scott Renaud and their student Florent Michel actually 6 years ago wrote a paper in which they made a theoretical model in which they tried to see what this would predict. This is a model in which there's only a one-dimensional condensate whose density is modulated, and they imposed periodic boundary conditions, which makes things a little easier. And what you see in the top line, the black curves, are these essentially the time of flight spectra. It is the number of particles as a function for different Ks for different durations of oscillation. And you see something that looks qualitatively like what we saw. That is to say, we see these peaks, and then they eventually start to broaden, although they broaden in this funny way that doesn't look exactly like the data. And finally, when you excite for long enough, they disappear altogether. The second line is the atomic correlation function, which I've written down here. It's the mean value of the product divided by the product of the mean values. And here they show that this correlation function for relatively short excitations is quite strong, and with time dissipates, so that at the end there's no correlation at all. And it seems to maybe, I don't know, it might dissipate more quickly than these density peaks do. And then they applied their own entanglement criterion, which amounts to using the Cauchy-Schwarz inequality, and asking whether this correlation function is greater than 2. And under the right circumstances, assuming the states are Gaussian, this inequality is well, yeah, if this number is bigger than 2, one can claim the state is entangled. So here is their theoretical prediction for this entanglement witness. And what you see is that for a certain duration of the oscillation. So this is plotted again in the number of oscillations to which the condensate has been subjected. And for a certain period, this witness actually does go above 2. That is to say, signaling an entangled state. And as you go longer, it dissipates. It eventually goes away to something that is not entangled, that is separable. And then there's an interesting thing here. One thing in the simulation also included the effects of finite temperature. So at very short times, I think we're seeing an effect of finite temperature because the process is starting from just a thermal ensemble, which is not entangled. So at these very early times, there has not yet been enough parametric excitation, parametric amplification to create entanglement. So qualitatively, this model looks pretty, seems to agree pretty well with this, with the observations we've made. And all this together has gotten us more and more confident about claiming that we have actually observed entangled phonons in this system. What's the next thing? Then there's a technical slide for people who really want to talk about correlation functions, but I think I want to skip that. I want to now just briefly mention what can happen when we try to push this even harder. You can try not even more and more excitations. And what you see in this set of data is that when we start exciting it even more, actually just a little bit longer than we had in the previous pictures we showed, we see a higher order peak at twice the k, corresponding to twice the k vector that we had initially. So there's some sort of higher order process happening, which may or may not be related to well, it's probably related to the interactions of these excitations with each other. And that may or may not be an interesting analog of what is called reheating in the cosmology parlance. This thing we can look at how much these things are all correlated. So here is a complicated graph showing a two-dimensional correlation function of all these k vectors. So what I'm showing you, the colors give you this correlation function. So once again, the average of the product, the mean of the product divided by the product of the means. And for two different k vectors, okay? And what you see is at a k vector such as this one here, this k vector is correlated, of course, with itself. There's some sort of thermal excitation. But there is also, this k vector is correlated with, what should I say? This k vector is correlated with minus k. What am I doing with this thing here? Minus k. It is correlated with minus 2k, and it's correlated with plus 2k. So we've got all these correlations happening at the same time. We have not spent a lot of time trying to uncover what all these correlations mean, but I think they're pretty interesting, and they're going to be interesting to study in more detail. And I should mention that we recently had a visit from Chen Qing in our lab, who's been observing similar higher order correlations in his experiment where he creates these jets. So I don't have any recent news from him, but I think there's a lot going on here that we'd like to study. And for future work, that's something that we, especially maybe Victor, if he has time, is going to want to look at. Okay, so I'm close to the end of what I was planning to say. In my concluding slide, I want to say, okay, if you buy my arguments that we have seen entangled phonons, you can ask, well, yeah, now so what? Personally, I find entangled phonons, the fact that this can happen, really cool, even though we're not really the first people to claim to have done so. Another thing that this does is it has taught a few atomic physicists about cosmology, working on this project, especially talking with people like Scott, Amory, and Renaud at the time, forced us to dip into the world of cosmology and learn a little about it. That's probably a good thing for the cosmologists, that the atomic physicists pay a little bit of attention to what they're doing. And then a larger question is, well, what have we, or what have the cosmologists learned about the early universe from this experiment? I don't know. Perhaps we are validating a preheating model. Maybe that's of interest. And maybe there are other things that actually, if the audience here has some idea, I'd like to hear about. One thing that I would say is that having done this experiment and getting a little more confident in the robustness of the result of the signals, I'm tempted to say that, yeah, this phenomenon is fairly robust and under a lot of experimental conditions. And although it's an awfully long extrapolation to extrapolate all the way back to the primordial universe, I want to say that this whole process, what we're learning is that it is robust, and ever since I've been started looking at it, it sounds a whole lot more credible than it did when all I knew about inflation was what I read in the popular press. It seemed kind of like science fiction to me a long time ago. But the whole story seems to hang together a little better, at least in my head, and that's part of the progress that we've made. So, but if any of you have some things to say about that, I'm very interested. And with that, I thank you for your attention, and I'm ready for any questions.
Thank you very much, Chris. It was a very nice presentation.